Welcome to The Explainer. Today we're cracking the case of a billion-dollar black box, a massive mystery hidden miles beneath our feet. Yep, we're going underground to see how engineers basically become detectives, solving a puzzle they can never, ever actually see.
I mean, think about it. This is the fundamental challenge. Imagine trying to map out a huge, complex cave system, but you can only do it from a single pinhole at the surface. That is the exact puzzle facing petroleum engineers. How in the world do you truly understand these vast, incredibly valuable oil and gas reservoirs that are completely invisible and totally inaccessible? And make no mistake, these reservoirs are immense assets. We're talking, quite literally, about billion-dollar black boxes. Figuring out what's inside isn't just some academic exercise. It is absolutely crucial for managing our energy resources and making really smart decisions for the future.
So how do you do it? How do you possibly get reliable information from a place that's buried under thousands of feet of solid rock? Well, the answer is a brilliant set of investigative techniques we call well testing. Okay, so let's dive into this. Honestly, the best way to think about well testing is like a police interrogation. Engineers can't see their suspect, the reservoir, but they can ask it questions and then analyze its answers to uncover its secrets. It is all about making the rocks talk.
So at its core, that's exactly what well testing is. It's a super sophisticated interrogation of both the well itself and that porous, kind of sponge-like rock formation it's drilled into. It's all about collecting the data to build a complete profile of our underground suspect.
And you know, just like in any good detective story, this investigation follows two very distinct but complementary lines of inquiry. Each one is designed to ask totally different questions and reveal different kinds of clues about what's really going on down there.
First up is what you might call the quick shakedown. This is productivity testing. It's focused, it's direct, and it's all about answering one simple but powerful question. What can this well give us right now? So the goals here are all about the immediate situation. First off, what is coming out of the pipe? Is it oil, gas, water, a mix? They'll grab samples to analyze in a lab. They'll also measure the pressure and temperature way down at the bottom of the well. But the main question, the big one, is how much can this well reliably produce? It's all about getting a quick snapshot of its current performance.
And the method is actually beautifully straightforward. Engineers let the well flow at a very controlled rate. Then they wait for the pressure deep down in the well to stabilize, and they record that number. Then they just change the flow rate, wait for it to stabilize again, and do it all over, building a dataset step by step.
Now, this is where it gets really interesting. When you plot those flow rates against the pressures you measured, you get a graph that tells a story. It's called the inflow performance relationship, or IPR, and it's basically a fundamental health check for the well. And the key clue from this IPR chart is a single number, the productivity index, or PI. Just think of it as the well's performance score. For an oil well, a nice, gentle slope on that graph means a high PI. That signifies an easy flow, a healthy, very productive well. It's exactly the result the detective wants to see.
On the other hand, if that line is super steep, that means a low PI. This tells our detective that the well is struggling. It has to work much, much harder to produce anything, which could be a sign of damage right around the well, or it could mean the rock itself has low permeability. It's just hard for fluids to flow through it. Either way, it's a critical diagnostic clue. Okay, let's move on to the second technique and see how this builds the case. If productivity testing was the quick shakedown, this is the deep forensic analysis. It's called descriptive testing, and it's designed to map out the reservoir's fundamental character and really the entire surrounding crime scene.
So how does this deep analysis even work? Well, instead of just measuring stable flow, the detective actually sends out a signal. The engineers create a sudden change in the production rate, which sends this pressure wave. It's like a sonar ping rippling out from the well, deep into the surrounding rock.
And by listening very carefully to the echo, that returning pressure signal, engineers can begin to map the unseen. This pressure wave, it'll bounce off boundaries, it gets distorted by faults, and it travels at different speeds through different types of rock. It reveals the reservoir's hidden geometry, its properties, and even whether it's connected to other wells nearby. It's incredible.
The data that comes back from this is just incredibly rich. When the engineers plot this returning pressure signal, the shape of the graph is totally unique. It acts like a fingerprint for that specific reservoir. No two are ever exactly alike, and this fingerprint holds all the clues to the mystery. And this right here, this is where the aha moment happens. By mathematically processing that pressure data, analysts create a second curve. It's called the derivative curve. And this curve has become what experts call the single most effective interpretation tool out there. It's basically the magnifying glass for this entire investigation.
So, what makes it so special? Well, the derivative curve essentially amplifies tiny, subtle changes in the pressure signal that are normally totally invisible. This extreme sensitivity makes a hidden fault line or a change in the rock quality suddenly pop out in the data, clear as day. It's like turning on a black light at a crime scene. It reveals details that were simply lost before.
So, when you put it all together, you can really start to see how these two detective methods, the quick shakedown and the deep forensic analysis, give engineers a complete picture of their underground asset. They can finally decode the reservoir story.
And this chart just summarizes it perfectly. You've got productivity testing, which assesses the well's immediate performance using stabilized flow, giving you that key productivity index. Then you have descriptive testing, which characterizes the entire reservoir using a pressure pulse, giving you that powerful derivative curve analysis. So, one tells you what you have right now. The other tells you about the size, shape, and long-term potential of the source itself.
And look, this isn't just some academic puzzle. Having this complete picture is what drives smarter, safer, and much more efficient decisions. By understanding the reservoir accurately, companies can prevent waste, maximize what they recover, and manage these critical energy resources responsibly. Ultimately, it's just a powerful reminder of human ingenuity, and it really makes you wonder, what other invisible worlds are we using clever science to map right now? From sending signals into the deepest parts of the ocean to listening for echoes from the farthest reaches of space, it seems our desire to explore the unknown truly knows no bounds.